So I'm John. I'm the CTO of Veridice, and I'm also a PhD student at UT Austin. And so I'm here to tell you about the automated detection of bugs within ZK circuits. And so first, let's just talk about how ZK circuits work. So essentially what's going to happen is you're going to have source code. It's going to be in some language like CIRCOM or Halo 2. And then that is going to be compiled down into two components. So essentially, you're going to compile it down, and you're going to get a set of constraints. These constraints then are going to be provided to your prover and your verifier. In addition, you're also going to have an implementation. So the implementation is going to be what's generating your witness. And so what you need to make sure, though, is that when you are designing these circuits, your implementation, so the witness generator, and your constraints are equivalent. There are some cases where certain applications might not need such a strong, they might not strictly need equivalence, but in many applications, they expect that their program is going to be deterministic, and so they want this equivalence within their circuit, and if they don't have it, then there's essentially a bug. And so first, let's talk about what equivalence even is. And so essentially, like we talked about before, you've got some program, which is your witness generator, which is going to take in some input, X, and it's going to output something, let's say, Y. Then in your constraints, it's going to take in both your inputs to your program and your outputs from that program. So it's going to take in X and Y, and it's just going to say one simple thing. Either, yes, this was verified, or no, it wasn't. And so what we want to make sure is that for every P of X is equal to Y, C of xy is accepted, or for every xy, P of x is equal to y if and only if C of xy is true. So basically, your program will only produce the outputs that are accepted by your constraints. And so that is essentially what we're saying here. And so essentially what we're going to talk about in this talk is how can this be violated and how can you automatically detect these violations. So for this, we have two requirements. So basically, for every input and output of P, we want to make sure that satisfies C. And then for all of the inputs and outputs that satisfy P, we need to make sure that they will be produced by your program. And so for that reason, we have two types of bugs here. We have over-constrained bugs, which occur when your constraints are more restrictive than your program. And so in most ZK languages, we don't actually care about these because the language itself will place any constraints in the program that are within your constraints. So we're going to ignore these for now, and we're going to instead focus on these under-constrained bugs. So what these under-constrained bugs do is they look for cases where your constraints are less restrictive than your program. So basically, they can take in inputs that were not produced by that program. So essentially, P of x does not produce y, but C of xy returns true. And so those are the particular types of bugs that we are concerned about here. So why do we care about this? Well, we've already taken a look at a ZK circuit, and essentially what's going to happen in this case is with these under-constrained bugs, the verifier can accept bad inputs. And so the reason why this is important is because we've seen a couple of hacks in the past where someone expected their circuits to be deterministic, but they weren't. So for example, Zcash or Tornado Cash ended up finding a bug within their circuit that allowed them to drain their own pool. Veridice has actually found bugs in CircomLib that omitted checks for the remainder, which would allow someone to manipulate math templates. And also, we've seen some other vulnerabilities in other applications. So what do we do? Well, let's first take a look at a particular example, which we'll use to motivate the problem. So here we have an adder. So this is just going to add 2 bits, and it's going to have an output, which is going to essentially be whether or not you need to carry to the next adder. And so here, things might look okay. So essentially what you do is you are doing bit arithmetic. You take in 2 inputs, those are your 2 bits, and then whether or not you had a carry from your previous adder, and then you've got outputs. And so basically what you're going to do in the computation that I just highlighted is you're going to compute the output bits. And so essentially this is going to be in your computation, goes into your witness, and it is essentially just saying that the output of your adder is consistent with the behavior of the adder of bits. And so then what you do next is you constrain those bits. And so you can see here that essentially what it's saying in both of those cases is that the output of the 2 bits, it has to be binary. And so we're going to see why this ends up causing a problem. And so in particular, I'll just point it out now, the reason why this is a problem is because this only specifies that the output bits are binary, but it doesn't actually specify what the value of those output bits are. So here we have a mismatch between the actual constraints and the implementation. So in order to detect this, we're going to look at one of the tools that Varedice has developed, which is Vanguard, and then later on we'll take a look at another tool really quickly because I probably won't have time to go into details. And so what Vanguard is going to do is it's going to take in your source code and it's going to feed that into Vanguard. And so Vanguard is the first static analyzer that finds discrepancies between your implementation and your computation. And so what Vanguard is going to do is it's going to take in your source code and it's going to check them against a whole bunch of these semantic patterns that we've created. And so these are the 8 in particular that we evaluated in a paper that we recently submitted. And you're going to get an output, which is, which particular detectors report violations. And so in addition, at the very end, I'll show a large evaluation where we evaluate each one of these detectors against a set of ZK circuits. So the way that we do this is when you feed an input into Vanguard, it's first going to construct what is called a circuit dependence graph. And so basically what a circuit dependence graph is going to do is it's going to be the core that's going to identify these discrepancies between your witness generator or your computation and the constraints. And so the way that it's going to do this is it's going to create a graph of the input program, and it's going to specifically represent 2 particular components. So if you're familiar with normal program analysis, essentially you should be familiar with something like a control flow graph and then a data flow graph. Here we're going to have a similar notion, but we're going to have where we have a data flow graph, so this is what this is going to do. It's going to represent the data flow within your witness generator, but in addition, we're also going to have a constraint graph. And so it is going to provide a relationship about which values have a constraint relationship among each other. And so maybe the easiest thing to do would be to show an example. So if we go back to that adder case, essentially if we create this CDG, what we're going to get is the following. So essentially we have 3 input signals and 2 output signals. And you can see here that something weird is happening where we have data flow from all of our inputs to the outputs, but we only have constraints on those outputs. And so this is something that we can identify with such a graph. And so why don't we now go and take a look at what we can learn from this graph in particular. So basically, we can look at those inputs and say, well, the inputs are never being constrained. They're never used in a constraint, which is something weird. And in some cases, so in some cases, if those were like the inputs to the circuit altogether, that could be a very large issue. Another thing that we can look at is we can see that we have under constrained outputs. And so the way that we detect this is we look at the outputs signals in particular, and we see if they are constrained in some way by the inputs. So they have to be transitively constrained by the inputs. In this case, they aren't. They are only being constrained by themselves. And so finally, we also can look at the conjunction of the data flow edges and the constraint edges, and we can say, well, the data flow edges are taking information from different sources than your constraint edges. So in this case, the constraint edges are only constraining the individual outputs, while the data flow in the witness generator is coming from all of your inputs. And so this signals that there might be something wrong with your circuit. And so we took all of these detectors that we wrote over this graph, and we performed an evaluation. So essentially, we evaluated against 258 circuits from 17 CIRCOM repositories available on GitHub, and we ended up getting the following results. And so just as a bit of an overview, essentially we found that some of the detectors that we wrote were very precise. So for example, the 3 that we have on the left are the under constrained output that we just looked at, and then the data flow constraint discrepancy, which is the 3rd one. So those were very accurate. And then we had a couple of others that were less accurate. However, one of the interesting things was 2 of the detectors that we wrote had a large false positive rate only because of two templates that were within circomlib. So essentially, once we whitelisted those templates, then the false positive rate of those detectors decreased dramatically. So essentially here, the blue part is the true positive, and for those 2 detectors, the yellow part is the false positive rate when you exclude those 2 templates, and then green is the total false positive rate. And so you can see here that each of the detectors have, most of the detectors have a relatively low false positive rate. And in addition, we ended up evaluating this over this large set of benchmarks, and we came to the conclusion that we had a 16.4% false positive rate. But also, this identified 34 bugs within our set of benchmarks, 32 of which were previously unknown vulnerabilities. And the interesting thing here is that the major source of those vulnerabilities came from this last detector, which is the divide by zero detector. And so one thing that shows is the divide by zero detector essentially looks for cases where you have something like multiplicative inverse computation, where you compute the multiplicative inverse of A and B. In that case, that operation is undefined when B is equal to 0, and when users use this particular operation, they forget to add a constraint that B could be equal to 0. And so in that case, this kind of shows that users have a hard time reasoning about the necessary constraints that need to be added to your constraint system in order to properly properly encode the equivalence between your computation and your constraint system. And so I quickly just want to end with another project, which I said I would speak about, but don't really have time to go into depth about, so if you have any questions about it, I can quickly answer those at the end. But essentially, we have another tool called Orca, which takes in a set of polynomial field constraints, and it outputs concrete evidence of whether a circuit is under constraint. And so it does this by producing 2 alternative witnesses, and so that are evaluated over the same inputs. So basically, for that reason, you have an under constrained circuit because they take in the same inputs, but they accept multiple outputs. And so essentially, the way that it works is it uses random mutations in order to attempt to find these output signals that could possibly accept, or that could accept multiple values for the same input. And then, when evaluating it, you can see if on the same example that we had before, you can see essentially what it outputs over on the right is 2 witnesses. So first there's a good witness that was provided by the user, and so that is going to have the expected behavior of your witness, and then the fuzzed witness, which essentially, in this case, just manipulates that carry out. So in this case, the original inputs were that B equals 1, or that B1 is 1, B2 is 0, carry is 0, and then the expected output is that V equals 1 and carry out is equal to 0, because that's the way a bit adder works. However, it's going to accept cases where carry out is either 0 or 1. And so that in particular is why this is buggy. And that happens in this case because they are only assigning to the witness generator here due to constraints in Circom partially. And as a result, they had to, let me go back. And so as a result, they had to write constraints that weren't necessarily correct. So in conclusion, I talked about 2 tools in this talk, so that was Orca and Vanguard. We also have another tool called Picus, if you're interested, which is currently open source and verifies whether or not your circuits are properly constrained. We also obviously perform audits, and so we've worked with a number of ZK protocols in this space, and those are some of them that we've worked with. And in addition, there's social information at the bottom if you're interested. Thank you.
Any questions for our speaker? you go back to that carry example? I'm trying to wrap my head around whether this is like a clearly circum is idiotic thing or just it's a misunderstanding. Like that left arrow, V left arrow, are you saying that doesn't even generate any constraint? That's
That
just
doesn't
like a
generate any
suggestion
constraints.
to
Yeah,
the-
that's something specific to Circom. So basically, in Circom, and maybe I should have made this a bit more clear in the beginning, you can only create constraints over anything or over anything that is quadratic. So basically, you have to have a quadratic equation on the right-hand side. And so in this case, because some of those are not quadratic, in particular, it doesn't like that mod in the first case. In the carry out case, technically, they could have used something that would generate constraints and also add the computation into their witness generator, but they didn't, and so.
So if that left arrow were a quadratic form on the right, it would have added a constraint? And because
So
it's not,
they expect the user to actually do this. The compiler will complain if, so basically the way that it works is there's 3 types of assignment here. So you have the equals equals equals, which generates a constraint. You have the arrow right there with 2 dashes, which only adds into your witness generator. And then finally you have arrow with 2 equals, which adds into both your constraints and your computation.
You should have to have like warning sign emoji in that symbol to, that's like, okay. Really cool.
Yeah, so they generate warnings now if you're using an operator and you could have used a stronger one, or if you're using that operator in a dangerous way. But sometimes you simply have to split up your computation in this way.
One quick comment on that question. This is actually necessary for optimization of some circuits. Like for instance, in field inversion, you want to do compute outside of generating constraints and then constrain later. For that topic, come to my talk in the afternoon. Any other questions for our speaker? We'll take one more.
Thank you for the talk. Having seen how automatic vulnerability detection works in Solidity, or in general smart contract languages, how much of the techniques that, for example, used in Slither are kind of carry over here, and how do you see more advanced developers kind of ending up using these tools? Because these detectors, sort of like the most advanced devs, it's sort of part of their normal workflow in Solidity.
Right.
Yeah.
Right. So in terms of what detectors we might be able to borrow from, let's say, something like Slither, unfortunately, because the execution model is extremely different, and in DeFi you have a lot of very different patterns you're looking for, it's unlikely that you're going to be able to migrate individual detectors over. Also, these languages are just a lot simpler in some ways than Solidity, because in Solidity you have to worry about things like external calls and stuff like that, where here all of the computation actually, as long as it ends up being compiled, becomes inline or straight line code, which is nice. And so I don't think that in terms of how users can use these tools, we expect that power users are going to want to use something similar to this, where in their development workflow, they can get quick feedback from something like a static analyzer, which is what we're generating here. And so, however, at the same time, with static analyzers similar to this, you get false positives, as I showed you previously. And so for that reason, we don't think that the end of the road is a static analyzer. You have to have more cases that can provide concrete feedback so that developers have a better way of determining whether or not something is a false positive. Does that kind of answer your question?